in RC circuit, we are going to determine the current charge in a circuit as a function of time. So first of all, what is the meaning of transient state? See, whenever a capacitor is connected across a battery, it takes some time to get fully charged. In this time interval, how the charge is changing on a capacitor, because of that, how the current is flowing in a circuit, that we are going to discuss here. In fact, capacitor take infinite amount or infinite time, or we can say capacitor basically never become fully charged, but the rate of charge on a capacitor gradually decreases as time increases. So we are going to discuss the current and charge in the circuit during the charging of a capacitor or during the discharging of a capacitor. So first case we can discuss growth of charge or we can say charging of a capacitor. Charging of a capacitor. So under this we are using the same concept here, Kirchhoff's law only, but only in which manner we are going to discuss those problems. See, this is a capacitor of capacitance C and resistor R. This is connected with a cell of EMF V. Initially switch S was open and capacitor was uncharged. So initially capacitor was uncharged. Capacitor was uncharged and switch S was open. Switch S was open. This is the initial condition. Now we would like to solve how the charge on capacitor changes with the time. Because of that, how the current changes in the circuit. See, at t is equal to 0, switch S close. At t is equal to 0, switch S close. What is the meaning of this? As soon as switch has been closed. So what I did here, by closing switch S, I connected a higher potential terminal of a cell with one of the plate of a battery and lower potential terminal of a cell with the another plate of a capacitor. Because of this potential difference between the electrodes of battery and plates of a capacitor, electrons start flowing from lower potential to higher potential. So electrons start flowing from this plate to this. Through the cell, electron will go in this plate. So this flow of charge will continue. And this flow of charge will continue till the potential of this plate and potential of this electrode are not become equal. When potential of this plate and electrodes are equal, then the flow of charge stop. So we are going to discuss in intermediate state, means before capacitor get fully charged, that state is called your transient state. So we can assume at t0 switch has closed. Now capacitor start charging. Capacitor start charging. In this process, electron flow from one plate of capacitor, electron flow from one plate of capacitor to another plate, to another plate through cell. This is the process. Now, let at T is equal to T, Q is the charge on capacitor, Q is the charge on capacitor, and I is the current in the circuit. So we can say let this is the charge Q and I is the current in the circuit at T is equal to T. Now, so first thing is that current. Current is defined as rate of flow of charge. The rate of flow of charge is nothing. It is the rate by which charge is coming on this plate. So, I can be written as dq by dt. This is the first equation we can write. Now, second equation. Second equation we can use Kirchhoff's second law. See, from here we can write here this minus q by c, then minus IR plus V, this is 0, or we can say here Q plus RC, and I value we can write dq by dt. dq by dt is equal to CV. This is your second equation. Now we can simplify this. From equation 2, we can simplify RC dq is equal to CV minus Q dt, dq by CV minus Q dt by RC. Now integrate. At T0, charge on the capacitor was 0. At T is equal to T, charge is Q. So this further we can write minus ln CV minus Q by CV is equal to minus T by RC. So after solving, we can have Q is equal to your CV 1 minus e to the power minus T by RC. This is the charge on capacitor. And current. I is written as dq by dt. So this gives us, just differentiate this one, we will get V by R e to the power minus T by RC. So this is the just a solution of this particular problem. So from here we can make a diagram how the charge is changing. So charge on capacitor changes like this, and after certain you can say time, charge on capacitor become maximum. That maximum charge we can say C into V, as we can hear. Similarly, if we are looking the graph for current versus time, so current is changing exponentially. So current versus time graph will be like this. So from the graph itself it is clear, charge on the capacitor here continuously increases and it will not come to at a final state, but as time increases, charge almost become your constant. So this is the equation. The main point here, making of equation is important. How to make equation? First, by using the definition of current. Current is your rate of flow of charge. Second, by using Kirchhoff law. So this is the solution of these two equations. And now from here so many other conclusion we can get. See. Now from this equation, Q is equal to CV, 1 minus e to the power minus T by RC, and I is equal to V by R to the power minus T by RC. What are the conclusion we can draw? First thing, as T increases, as T increases with time increases, charging process here increase. See, at T is equal to 0, it is called your initial state. Initial state means starting. At T is equal to 0, see, when we are substituting T value 0 here, e to the power 0 become your 1, charge on capacitor will be 0, but current in the circuit will be maximum. So at T0 initial state, charge on capacitor is 0 and current in the circuit here maximum. Current in the circuit is maximum. So what can be said here? So we can say, we can assume, if capacitor is initially uncharged, if capacitor is initially uncharged, then at T is equal to 0, capacitor can be taken as a short circuited. Capacitor can be taken as short circuited, or it can be replaced, or it can be replaced with a conducting wire. So at T0, at T is equal to 0, our circuit will be like this. This is your terminals of capacitor. Let A and B are terminal of capacitor. It can be taken like this. So now see here, the current in the circuit will be your V by R as per our expression is indicating. At T0, current will be your V by R. So at T0, if the capacitor is initially uncharged, so what can be done? It can be replaced with a simple conducting wire. So it is not having any resistance, not offered by any resistance, as well as there is no potential drop across the capacitor. All of the potential drop across the resistance. So current in the circuit will be maximum. Similarly, see, at T is equal to infinity, T infinity also represent like this: after a long time, or it is also called, or at steady state, T is equal to infinity, or after a long time, or at steady state. See here, T infinity. So when T infinity, e to the power value, this become your 0. So charge on capacitor your CV, which is nothing, it is the maximum charge, and current T infinity, e to the power minus infinity will be 0, so current will be 0. So at T is equal to infinity, or after a long time, or at steady state, charge on capacitor will be maximum, and there is no current. See, I0 value is coming, and there is no current in the circuit in which capacitor is connected. In which capacitor is connected. No current in the circuit in which capacitor is connected. So we can say, so capacitor can be treated as open circuited. Can be treated as an open circuit. So now at t is equal to infinity, our circuit diagram will be like this. See, A and B are the terminal of capacitor. So we can make a circuit diagram like this. At t is equal to your infinity. So since there is no current in the circuit because it is your open circuit, disconnected circuit. So for a current flow, circuit should be closed. So all the current, no current in the circuit, so all the potential drop of the voltage or of the cell will be across capacitors. That's why the charge on capacitor will be maximum. So what is the these 2 points? If the initial charge on capacitor is 0 or capacitor was uncharged initially, so at t is equal to 0 means initial state charge will remain 0, but at t infinity charge will be maximum. Then maximum situation means at t infinity, that is called steady state. Steady state means further flow of charge has been stopped. It means capacitor is now fully charged. When capacitor is fully charged, the further flow of charge will stop. That's why when further flow of charge stops, that's why charge is not flowing in the circuit and current in the circuit will be 0. So these two are the major outcome. So whenever we have to solve the problem, these 2 points we have to remember. If the capacitor is initially uncharged, so at t0 or initial state, you can replace the capacitor with a conducting wire, then your circuit will be easy. As well as if they are asking at steady state, so we can say the branch across which capacitor is connected, that branch can be taken as open circuited. Now see some other points related to this expression. Okay, now see the third point. In this expression, one term is your product of R and C. So the unit and dimension of product of R and C is the same as the unit and dimension of time. Unit and dimension of time. So this term is known as time constant. Time constant tau. So time constant tau can be written as time constant tau is equal to your R into C. So in terms of time constant, we can write charge is equal to CV 1 minus e to the power minus t by tau. Similarly, current we can write V by R e to the power minus t by tau. So this is the expression just in terms of time constant. How we can define? So let at t is equal to tau. It means when time is equal to tau, so how much charge? The Q will be your CV 1 minus e to the power minus 1. So this will be your CV 1 minus 1 by E. So when we are substituting the value of E, then we will get 0.639 into CV. And CV is what? Maximum charge. So this we can say 0.639 Q maximum. So we can define time constant is a time constant is a time in which charge on a capacitor becomes 63.9% of its maximum charge during charging of a capacitor. So this is the meaning of a time constant. So in general, time constant tau we can write R equivalent into C. By this relation, we can determine the time constant for any of the complicated circuit. So what is R equivalent? So where R equivalent is equivalent resistance across across the terminal of a capacitor, resistance across the terminal of capacitor, equivalent resistance of a circuit across the terminal of a capacitor after replacing cell with a wire. So from one example we can understand it in the better way. See, for example related to the time constant. See, the question is given like this. For example, this is the problem. Caption your C. Now question is that find time constant of a circuit. Then what you have to do? As per our expression, time constant written as R equivalent into C. So time constant tau is R equivalent into C. But what is the R equivalent? R equivalent is your equivalent resistance across the terminal of a capacitor. It means just remove the capacitor. So about this point we have to find the equivalent capacitance. So after replacing battery with a wire, our circuit diagram will be like this. R1, R2, this is your R3 and R4. So now from here these two are in parallel, then remaining circuit in series. So R equivalent will be here R1 plus R2 plus R3 R4 by R3 plus R4. So this is the R equivalent, and multiply with the capacitance C. So we can get the time constant tau value here like this. So these are some points related to your charging of a capacitor. Now come to the another point, decay of charge or discharging of a capacitor. Next is the decay of charge. Decay of charge, or we can say discharging of a capacitor. Discharging of capacitor. So we are having a capacitor which is already charged. Let this is the diagram, see. This is a capacitor of capacitance C. It has already charged Q0. Now this is connected with a resistor R and switch S. So capacitor is already charged. Now at t is equal to 0, switch S close. When switch S close, as soon as switch S close, it means what I did here, I connected these two plates of capacitor which were at different potential. So I have connected these two plates through a resistance R. Because of the difference in the potential in these two plates, charge starts flowing from one plate to another plate. So due to the flow of charge, current will develop and charge on the capacitor decreases. So let at t is equal to t, charge on capacitor is Q and current in the circuit is I. So at t is equal to t, we can have our diagram like this: Q charge, C capacitance, R resistance, and charge is flowing, so current like this. Now as current is decreasing, as capacitor is getting discharged, so current can be written as rate of flow of charge, and since charge is decreasing, so that can be written as I is equal to minus dq by dt. This is the first equation. Second, we can get again by using Kirchhoff's law here. So minus q by c, then plus IR equal to 0. This further we can write q by c is your I into R, and I we can written as minus dq by dt. Q is equal to RC and I is your minus dq by dt. Then this can be written as here dq by q is equal to minus dt by RC, and we can simplify. When t is equal to 0, at that time charge on the capacitor was Q0. When t is your t, charge is your Q. So this can be written as ln Q by Q0 is equal to minus T by RC, and this gives us relation Q is equal to Q0 minus T by RC, like this. And now the current relation, as I is your minus dq by dt, this we can get here Q0 by RC e to the power minus T by RC, like this. So if we are making a graph how the charge on a capacitor is decreasing, we can have a graph like this. Here charge is your maximum in the starting, which is our Q0, and similarly if we are looking at the graph for current versus time, that is also in the similar manner So initially your charge is, current is your maximum. This. So Q is your Q naught e to the power minus T by RC. And this further written as in terms of your time constant also. So in terms of time constant, charge can be said as Q naught e to the power minus T by tau. Now, if we are substituting T is equal to tau, then we will get charge of Q naught by E. In this form also we can define time constant. So we can write time constant is a time in which charge on a capacitor become 37% of maximum charge during discharging of a capacitor. So time constant we can write like this. So time constant, once again we can define time constant tau is a time in which charge on a capacitor become 37% of maximum charge during discharging of a capacitor. During discharging of capacitor. This is the definition of time constant in the terms of discharging of capacitor, and the previous definition was in terms of charging of a capacitor.